Okay, I think we can start. There's quite a few things to cover. I'll have office hours from 2 to 3 today, so if there's any sort of homework-related questions, we can take it there. I know there's been some confusion about the common mode rejection ratio in one of the problems. It's a little bit more kind of open-ended question than, you know, that everything is specified in text. So we can, I posted some hints online on Piazza, but if you want to sort of chat a little bit more about it specifically, I can talk about it 2 to 3 p.m. today. Sort of want to continue with the bipolar modeling stuff, and both kind of large signal, small signal models, as well as hopefully we'll get to biasing, and then that's kind of going to wrap up the bipolars. And hopefully next lecture we sort of go through the MOSFETs. So just to sort of recap real quick, where we left off was kind of the model for the bipolar transistor in the forward active region, which essentially boiled down to, in large signals, having around 0.7 volts of VBE voltage, and then having essentially a current-controlled current source of value beta IFB at the collector, where IB would be sort of the base current. And now from this, we're going to take a look at a few kind of second-order effects to complete the equations for the collector current, and then we're going to move into the small signal model. So one of the most dominant effects for the forward active regime is the early effect. And so what happens here is this is really the effect of VCE, which is the collector emitter voltage, on the characteristics of the collector current. If you take a look at the above model in the forward active region, really IC, which is this current over here, should not depend on VCE, which is the voltage between collector and emitter. That's usually our output voltage. So here I would say it's just beta F IB. So then my lines essentially of IC versus VCE versus the output should just be straight lines, right, that are characterized by what is the value of the base current, but nothing else, all the way till I get to this point of, let's say, 0.1 volt, where we said we enter saturation, right? And we're going to cover saturation as a region as well. But in forward active, which is this zone here, we shouldn't get any dependence on the output voltage. Of course, that's the ideal transistor. Now, what's really happening inside is that if you take a look, if you take a look at the drawings we had, sort of what's happening inside the base, we do have this depletion region between the base and the collector that depends on the voltage that is applied between base and the collector, so our VBC. Now, if I increase my output voltage, so if I increase the VCE, what happens with this VBC voltage? Well, if you take a look at what VCE is composed of, it's VBE plus VBC. Right. So there's one voltage source from emitter to base, and another voltage difference between base and the collector. So if I increase this, what happens with these two variables, VBE, or these two voltages, VBE and VBC? Does VBE increase? So I'm changing this voltage here. Does this voltage change? No. VB, it's very much pinned down to 0.7 volts. Anything happens in the circuit, if you move that by 0.2 volts, your IC is going to explode because it's an exponential. So what really is happening, this is, for all intents and purposes, pinned down to 0.7. So any change in VCE really reflects directly on the change in VBC. It's kind of almost the whole change drops on the base collector junction. Okay? So that means that anything we do to increase VCE, the voltage actually essentially changes right here across the junction. And what happens with PN junction when I apply more reverse biased voltage? What happens? Yeah, so depletion region gets bigger. So what happens is that my depletion region here broadens. So from something that was previously like this to something that is like that. Now, we had this minority carrier concentration that was NPB, right? From the slope of which we calculated what was essentially the collector current, diffusion current. So what's really happening here is if I shrink the base by extending the depletion region, my slope gets bigger. Because I have to pin down to 0 here in a shorter distance. Okay, so this is some VB prime. Okay. So if we take a look, just so remember, it was like AQ, the diffusion constant, and then there was this derivative. Right. So this derivative is essentially of this slope. So if my slope gets bigger, my IC, or my collector current, is going to get bigger. Meaning, if I have this room where the slope between the sand that's being built up on this one end and this is steeper, of course, it's going to the sand is going to tend to drift faster, right? So that's essentially what this is showing. So if this is really the case, and so we know what this factor is, we've derived it in the last lecture. So this is NAB times WB in VBE over VT. Now we can sort of go back and figure out, okay, given this, this change in delta VB, what is the impact of VCE on IC? So the way I'm going to do it is through simple differentiation. So I'm going to say delta IC is a change in the IC with respect to change in delta VCE. And then I want to say it's essentially an inverse change it's inversely proportional to the WB, simply because if I increase VCE, my width of the base is going to go down. And then I know that my IC is going to increase. Okay. So this is just math, okay? So now, but I can, from this math, figure out exactly what I want, and which is how I define this early voltage or the current curves. So what I'm going to say is that this early voltage is actually the intercept of IC and 0. So I have to take into account the slope, which is delta IC over VCE. And then from this equation here, I have IC, I have the gradient. So this is just going to be WB dVCE or dWB. And of course, because VCE, this delta VCE is really just delta VCB. Keep in mind that this is constant, right? Here, then this is just a change in the voltage applied to the junction versus the change of the junction. I can say it's minus VB 1 over change in base width, or change in the junction width, depletion width, over change in CB. And if you look in chapter 1, I don't want to sort of derive it here. There are equations for the width of the junction, PN junction in reverse bias versus the reverse bias voltage, right? And that's exactly what this factor is here. So if you go plug in kind of the width of the depletion junction will depend on the doping. So if you go plug the dopings in, typical for the collector and base, what you're going to see is that this VA is typically about 15 to 100 volts for the NPN transistors. Okay. So if you take a look now how the curve looks like, we previously said that, up to some very, very small voltage, which is 0.1 volts, all the curves should be flat. And they will just depend on, essentially, the DC bias current of the base. But really, what is happening is that there is this intersection voltage, minus VA. So all these curves will really have to pass through that point. Okay. So your real IC is this one over here. So this is the real piece. So then the equation for the current will be our old one plus this augmented triangle slope curve. And this is just simply VC over VA. So we're going to be using this when we go and derive small signal models, because that will also this dependence on the current on the output voltage will also give us this kind of R0 or the output impedance. Otherwise, we would be having infinite output impedance of the transistor, because the output current will not be changing based on the output voltage. Right? Okay, so I'm going to just briefly spend time on another region which we mentioned, and that's the saturation. In this region, we always classify it by kind of the junctions, a body, base emitter and base collector. And in this case, both are forward biased. So again, the curve is of IC versus VCE is that there is this very small region where currents really drop. This is about 0.1 to 0.2 volts. And all the currents that hit here will drop very abruptly . Very abruptly to 0. So this voltage is called VCES, or the saturation voltage. Now, all these derivations that we did for the current versus density, etc., once both junctions become forward biased, you no longer have this gradient in the base. You actually have flood of electrons from both sides. And therefore, really what matters is that VBE will be still approximately 0.7 volts. VCE is going to be somewhere between 0.1 to 0.2 volts. When which is the onset of the forward biasing of that base collector junction. And really, currents will be set by KVL and or KCL, essentially, and the outside biasing components. So you'll no longer have the beta factor between the base and the collector, but the base will be whatever the currents on the emitter and collector are, right? Okay. So now that we sort of went through at least sort of the most important modes of operation, so we had cutoff, we had forward, and saturation. The reverse active region is kind of similar, but we said that it's very inefficient because the ratios of the dopings are different. There are, though, symmetric PNP transistors and NPN in which the dopings are balanced, in which case the reverse beta will be kind of the same. But mostly people use the asymmetric so that you can handle larger VCE voltages without actually having a huge collector current modulation through the early voltage. Okay. So, because you saw that when we derived the early voltage, it really did depend on the dopings on both sides of the base and the collector. And by tweaking the collector doping, you can move the early voltage to be really big. And that's what you want for a good performance transistor. Okay. So we're going to go and look at small signal models now, and then hopefully get to some of the some biasing. So if we go and draw the transistor, and now sort of bias both the input and output. So this is, let's say, at VCC, and the input is both small signal biased and then large signal biased. This is 0.7. Then I have current IC capital is the bias current plus small signal current. And then also here, I'll have the IB, which is going to consist of the bias current and also the small signal current. If I try to describe transistor as sort of a 2 input ports and 2 output ports element, right? Because I have base emitter kind of difference, and then here collector emitter. Then I can sort of in general represent the 2-port models through the following kind of drawing. And this is, for example, called the Y model. And I'll say that this voltage is V1. It has a current of I1. And this voltage is V2. And the current is also I2. By the way, I'm writing voltages as plus minus V1. Then sometimes I get lazy, so it becomes just an arrow. Okay? And the head of the arrow means plus. So if you see that, don't be confused. That's not current flowing. That's just an arrow pointing from low potential to high potential in the circuit. Okay? And now we can name these conductances as 1 over Y11 and 1 over Y22. And then I'll write this guy as Y12V2. And then this will be Y21V1. Now notice in this model, information flows both ways, right? It flows from left to right, from V1 to V2, because V1 controls this current source. But it also flows this way because V2 controls this current source. Now, that's in a fully symmetric kind of system. Now, in the forward active region, I'm going to simplify this model. Of course, let me just write it out for you, how these are derived. So just looking at this figure, I can figure out what Y11 is, which is this resistor, by dividing I1 with V1 when this current source is not present, right? So to kill that current source, I have to say V2 equals 0. So then the test current that I push through, which is I1, develops V1 on this resistor, and then I know what that value is. So similarly, for Y22, I'll have also I2 over V2, but this current source has to be disabled, so V1 has to be equal to 0. Okay. So this is the general model. Now, disabling the reverse operation, we essentially get what we call a pi model, so in forward active region. The predominant flow of information is sort of from the base to the collector, and not the other way around, because the junction is biased like that. And so we have what we call a pi model, where we're going to just disable this V2 source. So we're going to have something called R pi, and then here we're going to have GM, R naught, base collector, and then this port will be the emitter. Okay? And then this voltage will be VBE, and then that voltage will develop or will control this current over here through GM VBE. Now this current will be IC, and this voltage VCE, and this will be I base. Okay. So the model parameters are R pi, which is our base transconductance or resistance, GM, and R naught. The rest, meaning GM, VBE, that's kind of a current control source. So let's try to figure out how do we extract these three parameters and what's their mutual dependence. So if I look again at these two port formulas here, then I can derive GM as IC over VBE, but under the condition that I short this output. Right? So if I short VCE, then no current will be flowing, meaning if I connect this node to this node, right? So if I make this connection over here, then I'm shorting this output resistor, R0. So 0 current flows through that. So all my current here, which is GMVBE, becomes essentially IC. Do you see that? OK. So that's why I can say that ICVBE is only for VCE equals 0. OK. And that's what we had in the model as Y21. Y21 was this transconductance over here. Now, IC and VBE are small signal values. It means they're derivatives or changes of the actual currents and voltages. So what I'm going to do to derive, I'm going to say GM equals an actual derivative of IC versus VBE. Notice that these are capital. So this is the changes in the total current versus total voltage. Right. And so I can do is delta VBE, and we know what our current is. I'm just going to write it without the early effect because I'm looking for changes in VBE, not in VCE. So that term doesn't really matter. And what I'm really going to get, because of this exponential, is just this. So what this means is this piece is really my IC. Then GM is equal to my IC, which is the bias current, over thermal voltage. Okay, and we already said VT is our KT over Q, right? So this is the first important relationship. It's a very simple relationship between the bias current on the collector and the VT. So then the second one that I have is the input resistance. Okay. And then again, just by the same token, how we did it for Y11 and Y22, what I have is that R pi is VBE over IB. So it's VBE over IB. Okay, but for VCE equals 0. That's just so I kill that other reverse path that in case it weakly exists, right? So again here, because these are small signal, this is just a change in the true VBE over I base, subject to VCE equals constant. So I don't want any effects from modulating that bias junction. And we'll see later where that actually comes into play. But normally, if you do change that reverse bias junction, you're changing kind of the slope and the total amount of the carriers in the base. So you are affecting some base current things like recombination current that we talked about. And so there is a sort of a side channel to attacking this number. Okay, so what this is going to end up being is delta VBE. And then here, I'm going to say, OK, this is my IC over beta naught. And that is beta naught over GM. So my total R pi is beta naught over GM. So that's the second important relationship. The third one, we're going to look at the output resistance. And again, if you take a look at the previous plot, if I want to extract R naught, I'm applying a test current at IC, and then I need to kill this current source so that all the current that goes from whatever the test voltage source here is goes through R naught, okay, and does not go through this current source. So that means I have to short VBE, make VBE 0 so that I disable this current source. Okay, so and that's exactly what we're going to write. So we're going to say this is our test voltage VCE over IC, subject to VBE being 0. And that's going to translate into changes in large signals, given that VBE equals constant. And again, now I can go and do a derivative on the full formula for the, so I can draw it as, this is 1 over delta IC over delta VCE. And we've already seen what this is, delta IC over VCE, right? When we talked about early voltage effects, that's exactly what we're looking for, right? So that will be 1 over off, and then we have this ISE VB over VT times 1 plus VCE over VA. Right. And if you go and do a little bit of calculus here, what you'll end up saying is that this is actually just VA over IC. So it's our early voltage divided by the current. So again, very simple relationship. Of course, this is all for VB equals constant. Okay. So just to show you real quick that things are actually pretty similar for a PNP transistor. We actually haven't talked much about it, but I just want to sketch it here. PNP just means that our emitter base collector are now PNP, which means that now we have acceptors here and donors in the base. And for homework, you have some stuff to calculate like that. So all the stuff, all the principles we've done for the NPN should be applicable. It's just that now, maybe you don't have electron currents, but you have holes currents and things like that. But everything is kind of equivalent. So it will jog your brains a little bit, but hopefully not too much. Okay. So the key thing here is that it's really easy to work with PNPs just as long as you always keep that kind of oriented the right way and with right voltages. So currents always kind of flow down through your circuit, and voltages always kind of point up from between 0 and your VCC. And so that's how we're going to really orient this. So this is IB. Now we're drawing this as current flowing not from the emitter, away from the emitter, but into the emitter, right? And that's a difference between the PNP and NPN. And also, I'm gonna draw the model as R pi. So I'm drawing the base current as coming out. C terminal. I'm also drawing the C out, okay, just because my emitter current is going in. And then I have here VEB, and I'm going to then do GM VEB. So this is just to kind of make it easier for you to go through the circuit and evaluate things. So in summary, for small signals, these rudimentary small signals, we had sort of GM times R pi equals beta naught, and GM is sort of IC over VT. And then we had R naught, which was VA over IC. Right? Okay. Those are pretty much all the parameters you'll need for very quick and dirty kind of small signal analysis. That's kind of around DC gain and understanding what happens in DC. Now, in reality, actually, the situation is a lot more complex. And this is sort of a picture from the book where we said, hey, my transistor is right here. This is my N plus PN region. And then all the things that we've been talking about are for this main current flow, right? Stuff that's happening between emitter, base, and collector. Fortunately, in real life, there's all this other junk around it. And you have to really, some of it really affects you a lot, and you'll have to understand what it is. And some of these things you're not going to see at DC, but as you start moving electrons faster, as sort of small signal, you apply like a AC source, very small amplitude here, and you're looking at electron fluctuations, which means your current at the output. Well, at some frequency, you may start noticing some of the effects, especially some of the parasitic capacitance effects. So if we take a look at how I can map all these other things around into small signal, so this is a more complete model. Now you're going to start seeing some additions to kind of what we talked about. So the first piece is here in the base, I have this long path for current or to come from the base and hit this region of main region of action. Right? And that path, you know, our base is lightly doped than the collector than the emitter, so there will be some resistivity in that path. And we're going to mark that as RB. The potential that really sets the action inside the transistor is the potential right here. It's not the potential we apply over here. So if there is some R that's built in here, that will result in the IR drop between the base contact point and this effective base region. So we can call this B prime and this B. Right? So we're going to say, OK, well, that's this B prime. And that potential is really the one that affects my current gain and things like that. So from that point, I'm going to have my R pi. I'm adding here another piece that we'll talk in just a second, which is C pi. And then on the other side, OK, I have my standard GM VBE, and then R naught. But I also have two other terms that I need to address. Okay. So these three pieces, which are R mu, C mu, and C pi, are new. Okay. So C mu is this capacitance over here, which is the capacitance between the base and the collector. In forward active region, what is the state of that junction? Forward, reverse, what do you think? Between base and collector. In the forward active region, what is that junction? Reverse bias, right. So when things are changing in the circuit, meaning when I'm changing VCE, that reverse bias value is changing. So the depletion region is fluctuating, and it contains some charge, right? So what I have is EBC, and then there is this depletion region here where donors have given an electron and are left with positive charge, and acceptors have accepted an electron and are now left with negative charge. And that built-in depletion capacitor is really my parasitic capacitor between base and collector. And because of the geometry of the transistor, in this small region, it's really small, right? But there's this whole sidewall that actually is also biased, right? So that whole sidewall is adding a lot of this base collector capacitance, because my depletion region exists like all around here, right? Okay. Now, sort of early in chapter 1, when you look at p-n junction, there's some routine derivation from for C mu. So we'll call this base collector depletion cap. And there is some zero bias kind of capacitance. And then, of course, as I'm applying bigger voltage to collector-base junction, that depletion region is expanding. So my capacitance actually drops, right? Because I'm expanding the distance between the two plates in the capacitor. And then this phi is kind of my built-in potential. And just for completeness, this kind of depends on the acceptors in the base and donors in the collector, and then I squared that. Oops. That kind of stuff. Okay. And then also my C mu is kind of proportional to these are all standard p-n junction formulas, so just so you have it for completeness. Now, just want to discuss a little bit this C mu because it's kind of interesting what's happening. This is base collector. This is C mu. So up until, if you look at that equation, it's sort of as the difference is changing, this cap is kind of increasing. Okay? But of course, when VBC becomes exactly size 0 or minus size 0, you have, because this is VBC, this was VCB, you would have infinity, right? But that doesn't happen. Why doesn't it happen? This is just a curve for the reverse bias depletion cap. But if I'm entering forward bias, I'm getting a lot more minority carriers around the junction, right? And so my previous understanding that there's nothing else except the donors and acceptors forming the field is not correct. And so I have to take into account that other minority charge, and therefore it more becomes like a junction, PN forward biased PN junction capacitance. So after this point, really what's happening, the cap starts going down. Because this formula no longer applies. Basically up to here, which is size 0 over 2, I can still kind of use these equations because there's not a lot of buildup of the charge. But after that, really, I can't. Okay. And what I can use, though, is some stuff that in this region, it's kind of the junction cap. Just to show you real quick over here. Okay. Another kind of cap that we didn't capture, and that's the one that, oops, I think I had it somewhere. Doesn't matter. It was C pi, yeah, here, C pi in the model. And so that C pi cap is really the cap between base and the emitter. And now you're going to see, this cap is exactly, because a base emitter junction is forward bias, this cap is exactly all about how the minority carriers are fluctuating around the junction in time. Right. So we do have it as kind of a sum of two caps. One is the junction capacitance, and that's called CJE. Here on the figure, that's this piece. Right. So that's the same depletion, just like what we derived right now. It's just that because that junction is in forward bias, it's sort of kind of stuck here, somewhere around here, right? Now, as I said, the much bigger one that really dictates everything is this diffusion capacitance. And to really understand how what it represents, we're going to say that anytime we inject the electron into the base, it sort of rushes through the base with some speed, right? So spends some time in the base. And I can sort of calculate what that speed is by saying, oh, hey, I have a total charge, total number of electrons. So this is charge in transit. And then I divide that by the total current that I see in the collector. current is charge per unit of time, right? So this exactly gives me sort of the speed of transit, how much or how fast are electrons flowing through that part. And then, of course, I can now go and approximate and say that I'm really looking for small changes. So delta QE per delta IC. And from here, QE, which is a small change, is going to be equal to tau f times a small change in IC. Right. Because QE is charge, I can also represent charge as CV. Right. Some voltage and some capacitance. And that's that junction capacitance that I care about. So I'm going to say this is my junction, CB, and but just diffusion component, times VBE, which is the voltage across the junction. And then from here, I can derive what that CB really is. So CB is really tau f times IC over VBE. And then guess what? IC over VBE, well, that's just my GM. Right? So tau f, CB is really tau f times GM. Now, C pi is approximately CB because we sort of disregarded this junction cap is like much smaller than CB. This junction cap was sort of the side wall capacitance of the junction. Okay, so there's just one more thing left on this more complex model. And that's the so-called bridge resistance between, so this is this bridge R mu between the collector and the base. And now, because this is a PN junction, there's really no resistance per se, but this is kind of the effective resistance. And what I mean by this is that if I look at the change in VCE over the change in IRB, let's just do it right. So change in VCE versus change in IRB. You remember what IRB was? That was the recombination current in the base, meaning that small branch of electrons that gets compensated by the holes or recombined in the base. So that's delta VCE over, now I can just manipulate this as, and essentially to try to figure out what is, so this I know what it is. That's R naught. And then here I'm trying to figure out the ratio of the change in IC versus IRB. If I was looking at a change of IC over I base, then I know that's beta 0. Right? So delta IC over delta IB, we already know that's beta 0. So I need to figure out what this is. Is this bigger or smaller than beta 0? What do you think? What constitutes the base current? Recombination current and what else? There was another. So there's, as electrons are coming into the base, holes are coming into the base, right? There's one component that clashes here and annihilates the electrons. And then there's another component that does what? Where does it go? So this is the base. Emitter, collector. Where does that other component go? It's not, collector is reverse bias, so it's not going to let you go there. Where is it easy to slide? You can't go in the reverse bias because there's a potential barrier. But on the other side, what is on the other side? base emitter is forward biased, so the holes hop there. So I have this current, which is the holes diffusion current in the emitter, and the recombination. And we said last lecture which one is much bigger than the other. The emitter current, yes. So this was IPE, and this was IRB. And this one was much bigger than this one. So if the sum of them is the base, but here I'm looking at the ratio of collector to a smaller component, then this one is bigger than this one, right? And so in reality, this is approximately 10 beta 0. Something like that in NPN. So this is like essentially 10 beta 0 R0. And this is all because IPE is much bigger than the recombination. Okay. Okay, let me spend one more minute on the biasing because it may actually help you a little bit for the homework, just to understand a few basic things, and then I'll let you go. When you solve problems with biasing in BJTs, you have to sometimes make some assumptions and kind of later verify that they're true. And so what you're going to see is that, for example, you're always going to say, OK, let me figure out whether this transistor is in forward active region. So if it is, then this must be 0.7 volts. And then I go figure out how the rest of the currents and voltages are stacking with this junction being pinned down to 0.7. And once I'm done, I sort of check whether this piece is bigger than 0.2 volts. If it is, then my assumption was correct because I'm not in saturation. Right? Or you can impose this as additional condition and then solve for all the resistors and currents to make that happen. Right? Then you're designing on purpose all the biasing to be in the forward active region. So a couple of schemes to realize the biasing, for example, would be RB, RC, and then you have VCC, and then you have here C base that goes to infinity, and then you have here just your small signal source that is alternating current. So it goes easily through the capacitor, but does not change the DC value of this point. The problem with this arrangement is threefold. Okay? So problems. One, my IC depends on beta F. Right? Direct ratio of the base current and the second is that it's VCC dependent. Very strongly. If VCC changes, this thing here changes quite a bit, which is my VBE. So I'm really sensitive, exponentially sensitive to VCC. Right? And another one is there is this thermal runaway concept that if temperature increases, my collector current increases, okay? Because the leakage current in the collector, if you disconnect the base, the leakage current in the collector, that reverse bias junction, will increase with temperature. And that one gets multiplied by the beta factor, so that leakage. So you essentially get, again, that because of that increase in IC, temperature increases, and then again, this increases and your transistor explodes. Okay, so you can do this a few times in the lab, and you'll see what I'm talking about. Now, alternative scheme is to kind of do this, and I'll do this just real quick. Okay. Now I'm sort of